Okay, good afternoon. Welcome to the last in a series of 6 lectures on sustainability lifecycle analysis. And we're going to conclude this afternoon with a short discussion of Exergy, and I'll explain what that is, and hopefully you'll ask me a lot of questions. If you already know what it is, then maybe you'll ask me tough questions associated with it. So let's go ahead and launch into that. But let's first begin just by looking at a simple input-output energy diagram. It's a Sankey diagram, and I'll finish up with some amusing comments on that at the end of the talk. But this is done by a chap named O'Brien from Ottawa. It's one of these things that's published online, but it's a verifiable energy balance for a house over a midwinter week in Ottawa. It's a steady state, so that the house is maintained at a steady state temperature. And so, of course, we know from the first law of thermodynamics that under those cases, if the house isn't heating up or cooling down, that the energy that goes in is equal to the energy out. And again, that reinforces what we discussed last time, that energy is conserved. So when sometimes in the popular press they talk about energy conservation, they're not really talking about that. And during the course of this lecture, maybe we'll understand what we actually are talking about. I think you guys already, in a sense, know. If we write down the energy balance for that, we know that what goes in must come out, because we can't create or destroy energy. So in steady state, that's the case. And we also learned last time that in steady state, the rate of change of entropy in the system is 0 if it's steady state. And that means that let me use my pointer for this, if I can find it, there it is. That if we look at an entropy balance, what goes out equal what goes in plus entropy generated during the process. And we know that this entropy generated here has something to do with irreversibility in the system, and that we have a sense that the larger the irreversibility, perhaps the more inefficiencies there are in our process. Is there something that we can do about that? Okay. And just to say, if we could just reuse all the output energy, we wouldn't have any problems whatsoever, right? We'd be in great shape. And it turns out that we can't. We can't really tell why from here, but we can do a combination, if you like, of thinking about entropy generation, thinking about an energy balance that would motivate that, okay? So because we generate this entropy, the energy and mass in our outputs, right, must have something that gets thrown away, doesn't get reused, all right? And so this motivates a quantity that we call exergy. So again, the energy content of the universe is constant. We've got it, right? It's not going to change. We simply transfer it from one form to another. We move it around. We're interested in energy that we can use to do something useful. And so, I forget who it was, and I think it was a guy named Rant came up with a concept of something called exergy, which is the useful work potential of energy. So if we see energy around, they say, how much of that can we actually use? Can we do work with it that we want to do? Exergy, that useful quantity of energy that we use to do useful work, is not conserved. Okay? And also, once we destroy exergy in a process, we never get it back. So useful energy that you destroy in a process is unrecoverable. And so this is interesting, because now if we do, and we'll look at a couple of examples of this, an exergy analysis of a system, which we'll talk about a little bit later on, we may be able to identify where we can improve a process. A simple energy analysis may show us that. It may not, because it may hide in the output energy what's useful output energy and what isn't. Okay, so a simple example might be recovering waste heat from a power station and putting it to good use. You already know you can't use all of it. So how much of it can you put to good use? Because there must be some useful output energy for that. Okay, so now let's go back and sort of consider what actually exergy is. Okay, so we say its definition, it's just energy extracted as useful work. We call it exergy. It's a property of the system because energy is a property. Any system that's in complete equilibrium with its surroundings, so there's no temperature differential anywhere across the system, this has zero exergy. And we say that that particular system, which is completely equilibrated with the surroundings, nothing can happen, is in a dead state. Because how'd you get it out of it? You'd have to do something to it. You'd have to change that system to do work on it. The exergy of the thermal energy of a reservoir, we can say is equivalent to the theoretical work output of a Carnot heat engine, and I'll remind you what that is in a second, that operates between a reservoir and the environment. Okay? So for example, we see here a hot reservoir in red here, a cold one. This can be our surroundings if you like. We supply heat reversibly from here at this temperature TH to the heat engine, and then the other side of the system we supply heat from the heat engine to the reservoir, again reversibly to this cold reservoir here, and during the cycle there's net work that's put out. And we talked last time about the efficiency of such a cycle, and we determined that the theoretical reversible cycle efficiency, this Carnot heat engine, is actually equal to the reversible heat input from the hot reservoir multiplied by a quantity which involves subtracting the ratio of the cold reservoir to the hot reservoir temperature from 1. And then just to remind you last time, so if we have any heat engine, then its theoretical efficiency is simply you take 1 and you subtract the ratio of the heat output to the heat input. So your waste heat to the heat you put into the system. If it's a reversible heat engine, that translates directly to the ratio of the cold to hot temperature, reservoir temperatures. And by the way, don't forget that these things are in Kelvin, the absolute temperatures, otherwise you'll get a horribly wrong efficiency answer, okay? So don't forget that, they're absolute temperatures. And if you're really interested and you hadn't covered that in previous thermodynamics classes, it's interesting to go back and look at the literature of the time which led to the definition of an absolute temperature. It came from people working on the second law, people like Kelvin, hence the name for the unit of temperature, okay, who worked on that, okay. Let's just look at some familiar forms of energy. You're all familiar, everyone knows, you know, a half V squared is the kinetic energy per unit mass. All of that kinetic energy is available to do work. So kinetic energy is its own exergy. It's the same, exergy of kinetic energy has the same value. Now that doesn't guarantee when you convert it that you'll convert it that efficiently, right? You may waste exergy in the process, but it's all available. The same is true of potential energy. So here's our potential energy per unit mass, all available to do useful work. Now it just depends on how we do that conversion. Notice that both of these quantities are independent of temperature and pressure of whatever the environment is. Now the conversion process may be dependent on that, but those energy quantities are independent of it. So when we talk about useful work, and please interrupt me if this isn't clear. I can't, here it is. I'm having problems controlling this arrow. So I've said before, the work that's done in a system is not necessarily usable. So we can draw this simple little cartoon here, where we have a piston operating in conjunction with a heat engine that's dumping heat to an environment at some temperature T0. Here's the incremental heat transfer delta Q here. And we can look at the work associated with this piston, and we can describe it as PDV work. So as the gas expands, it does work on these surroundings. It does work according to PDV, and it does work on the surroundings according to P naught dV, where P naught is the pressure of the surroundings here. Okay? The useful work that's done is done by the gauge pressure difference, right? The actual difference between whatever this pressure is here, going through the expansion process, and the ambient pressure out here, the gauge pressure. So it's that's the useful work. The work that's done on the surroundings is simply, this is a constant pressure, so it's just the pressure difference here times the volume change, right? So useful work is just the difference between the total work done by that piston and the work done by the piston on the surroundings. So we could, if we like, just write it out this way. And this is not a bad, introductory thermo textbook. It's undergraduate level, but it does a nice job of explaining very simply, very pictorially, a lot of these concepts. So if you want to review it, that's one good one. It seems to be becoming a standard in many undergraduate institutions. Okay. It's worth talking here about reversible work. Whenever we deal with thermodynamics, we always run to some idealization where we can do processes reversibly, even though we know in reality we can't, because it just allows us to do little mind experiments and then better understand the real world in terms of what isn't reversible. Okay, so it gives us some reference. And we say that reversible work is the maximum amount of useful work that can be produced, or, depending on the device, the minimum work that needs to be supplied to any system as it undergoes some process between a specific initial and final state, or even through a cycle. Okay? And so, but for example, when I say needs to be supplied, we might be talking about using a heat pump, which of course doesn't output work, outputs heat. Or we might be talking about a power station which outputs work. Okay, so you sometimes have to keep those in mind. I'm not sure why this is a bit messed up here, but we'll deal with it. So reversible work is useful work output or input obtained when the process between the initial and final states is executed in a totally reversible manner. Okay? So useful and reversible work terms are identical. Right? Reversible work, there's no irreversibilities. I don't lose anything, I can do it. So irreversibility is the difference between the useful work and the reversible work. And that irreversibility is equal to the amount of exergy we destroyed. So we have a certain amount of work that's available to be done by that system's energy. And theoretically, if it was a reversible process, all of it would be reversible work. But there's reversibilities in the system, so when we subtract the actual work done from the reversible work done, that's the irreversibility that was lost. But in principle, the reversible exergy was all the stuff that we could have had in there. Okay? And we can calculate it. It turns out that what you destroy is equal to the temperature of this environment, the external environment here, times the generated entropy. It's equal to the reversible work out minus the available work, useful work out, which is less than for a real process, which is less than that. Or if you've got a device where you're putting work in, so it's a heat exchanger, it's a heat pump or something like that, then it's the useful work in minus the reversible work in. Okay, so because you put more work into your irreversible heat pump than you would in a reversible one. So then that difference is what you lose. And quite clearly, when the system's reversible, you don't destroy any exergy. Okay? And Sgen here is the entropy generated during the process. And so we can think about the irreversibility in the system now in terms of wasted work potential, all right, or lost opportunity to do work. Once we've destroyed that exergy, we can't ever have it back. And so we're really wasting a resource there. Unlike when we talked about energy, because of course you can't destroy energy, but you can destroy useful energy in a sense, which is what we're talking about with exergy. And I should tell you at this point, I've always been kind of skeptical about using exergy because I always think you can deal with things in terms of energy and entropy. But we'll see in a minute when you are looking at some aspects of a system with a view to analyzing how efficient is this really? I mean, in a practical sense. Or where can I make improvements that are real in this system that are going to lead to a cost savings, a savings in the amount of energy that's actually used to do the same process. That's when Exergy can become useful for comparative purposes. So don't get wholly seduced by it, because in many instances you can do what you need to do just by looking at energy, just by looking at entropy. But one might argue that, the second law and entropy simply tell you what's possible in a process. And I know that very often we get to determine, someone comes along with a new idea, you're sent the idea to evaluate by some organization, and the first thing I always look to save time is there a clear violation of the second law of thermodynamics? Because if I can do that in 3 lines, I can still charge them the same consulting fee, and I've saved myself a whole bunch of time, right? And so the first thing you look for, so I think I might have mentioned it last time, I've been sent things like, oh, here's a heat pump that uses Lake Erie. It was like more like a Lake Erie power station. It was using that as the heat source. And the argument made by the guys, there's a lot of energy in the lake, and that's true, because water has quite a high internal energy. It's got a very high heat capacity. But it's not necessarily true that that's a great way to have a power station. There are ocean thermal power stations where they have a reasonable temperature difference, but typically their efficiencies are on the order of, like Carnot efficiencies now. The theoretical reversible ones are about 8%. And when you do it in reality, you find that you can't make them work. Well, I had one to design where I look around, I cannot find the cold reservoir. It's not there. It's not rejecting any heat anywhere. And so now I can say, well, this is thermodynamics 202 or whatever, a heat engine that operates in conjunction with a single thermal reservoir cannot output net work, period. So I can't do anything with that. And so I don't even have to do a calculation to show that it's a completely impossible system, right? So you can evaluate something's qualitative. Now, if you may find that looks like it's possible, right? So maybe it does have to. Then you actually have to do the numbers. And what usually happens is you may find it satisfies an energy balance, and that's usually reasonable to do. But an impossible process can satisfy an energy balance. But an impossible process cannot have positive entropy. If you look at it, if your generated entropy, which always has to be positive, if it came out to be negative, you say, well, this can't work. Right? So you'd apply your entropy balance to it, and it would tell you either satisfied or haven't. You have all the numbers for it. There's no unknowns. So there'd be an inconsistency in there. Okay.
There is an entropy change even with the Carnot cycle. Is that included in S-Gen?
Well, there's no irreversibilities. It's totally reversible. Carnot is totally internally reversible. It's theoretical.
Isn't there still a delta S in the Carnot cycle?
No, well, this is through pieces of the devices, but through the cycle, no, because you come back to the same state, right? So you start off in state 1, right, and you supply the heat, then you go down with the adiabatic cooling, then you dump the excess heat, and then you compress, you come back up to the water state, and then you turn it to steam. And so there's no net change in entropy because it's reversible. So the easiest way, if you looked at it on a TS diagram, it's a square, okay, with S along the bottom. And then if you look at TS with reversible, always kicks out the entropy increases, right? So as you come down that adiabatic part, it swings out to the right, and you get a little delta S in there.
That's why I'm a little rusty.
It's all right. Okay, so it turns out we talked about the Carnot efficiency, and let me just not risk you forgetting. So the Carnot efficiency was this, I keep using my finger, was this thing here. So it's 1 minus the ratio of the cold to hot temperatures, all right? And then this thermal efficiency was 1 minus the ratio of the heat output, heat input, okay? And there's other things we can do with refrigerators and things like that, but I'm not going to talk about that now. But we can look at a different way of looking at this. And so we call it a second law efficiency, where we take our ratio of our theoretical efficiency to the theoretical reversible efficiency. So this is the one to remember. So you can say, this is my useful work out. This is my reversible work out. Okay? So this is a system which has irreversibilities. This is work done by the system that is reversible. if we have work-producing devices. If there works like heat pumps, refrigerators, we switch this around, and we have the efficiency, second law efficiency, is the reversible work divided by the irreversible work put in, okay? And we can look at it another way. Exergy recovered divided by exergy supplied. Okay. That's equal to 1 minus exergy destroyed by exergy supplied, by definition. So we'll come back and we'll use that efficiency a little later. Let's look at an exergy change in a system and go through it relatively slowly. And so I'll try to slow down a little bit here. So again, we'll go back to this little simple device here. We have a piston, a heat engine, reservoir here, and we're looking at the incremental works of these things. And we're looking at this heat transfer across here. When heat's transferred to or from a closed system and there's a temperature difference across the boundary, the exergy for the system can be determined by looking at how much of the heat transfer is converted to work. And of course, this is every time you do a real system like that, it's going to happen. Okay? So if we take the heat transfer to be from the system to its surroundings, right, the conservation of energy is the change of energy in minus the change of energy out is the change of energy of the system. And this is incrementally as we go through the cycle. All right? So we can write this in this way, and we've taken the heat transfer to be from the system to its surroundings. So I have internal energy here, incremental work output, incremental heat input to the system from its surroundings. And then the incremental work, as we discussed before, here is equal to PdV. That's equal to the actual useful work done plus the work done to the surroundings. So we can describe it like that. We want some reversibility in the process, so we have a reversible heat engine here. And this reversible heat engine is equal to, the work done is equal to the theoretical efficiency times the incremental heat input to the engine. You can write it this way. So T naught is surrounding temperatures. T is the temperature now that we're operating the piston. Okay, so we've got this relationship here. There's a change in entropy, which is equal to minus delta Q over T. That's the net entropy change, again, incrementally during this process. And if we manipulate these two expressions and arrange them in this way, we can express the internal energy as these two differences here. And we can rearrange to find total useful work being the sum of the incremental useful work plus the incremental work done by the reversible heat engine. And that's equal to the change in the minus the change in the total internal energy minus the work done on the surroundings by the pistons plus T naught times the entropy change. And we can have a total amount done, useful. And so this is our, for, if you like, a closed system, which looks like this. It's minus du. So we go from u naught to some system u. So all this is compared to the internal energy of the surroundings here. Okay, so this is the total exergy here, is the total work due to a system undergoing a reversible process from some given state to the dead state. So the dead state is this environmental state in here. It's isolated by itself, it's not doing anything. And so that's the internal energy there, that's its volume, so on and so forth. The energy, exergy of a closed system, you can add in its potential and its potential energy and its kinetic energy in here, or you can write them out in these per unit mass quantities here. So, and as we discussed earlier, all the kinetic and all the potential energy is available to do work. Now it's up to you to find a process where you can extract the maximum out. Since we're dealing with systems that are not closed, very often there are flows going in and out. We can talk about flow exergy. And flow exergy is really simply, as you might express, really related to the energy needed to push the mass through in and out of a control volume. And it's simply the difference between the actual pressure and the environmental pressure, or gauge pressure here, multiplied by the density. So the specific volume, I should say, 1 over the density. And then we can add up the exergy for a flowing fluid per unit mass, looks like this, or we simply added in the flow work up in here. As much as we did with the energy analysis. Remember, we dealt with that, and we can call it a stream enthalpy. We can use enthalpy in here because we've got this these PV terms in here. We can define the specific enthalpy and write it out this way. And what's different then in here is this quantity in here with our exergy, and it's related to the temperature of the surroundings multiplied by the change in entropy from the entropy of the surrounding. Okay, we talked about energy transfer. We can transfer energy by heat, work, and mass, and exergy is a form of energy, obviously, so we can obviously do that. We talked about it before, we just defined it again. Exergy transferred by heat can be calculated simply by taking the heat flux, all right, here, and multiplying it by 1 minus the ratio of the environmental temperature to the actual temperature of the surrounding temperature to the temperature of your system. For example, let's say, you're looking at heat passing through a wall. So you have a temperature here up at T1. We have a gradient through the wall and a lower temperature here, let's say T2. And in steady state, so if this gradient is now that the straight line is for a uniform medium, that's the straight line slope is the solution to the heat equation for constant properties. Then you would just balance the heat fluxes. So this is your energy analysis through here. It doesn't really tell us very much other than the energy goes in is equal to the energy comes out, and this is maintained as a constant temperature at this point here, and at every point in the interior is constant but different, and has a linear relationship with distance away from the hot wall here. And we look at the entropy transfer through here. You'd look at the Q divided by T1. The Q's are the same, but T2 is smaller here. Q divided by T2 is bigger. The difference is the entropy generated in the process, because when you have heat transfer across a temperature difference, it's an irreversible process, because you cannot make the heat go the other way from cold to hot. It's an irreversible process, so you will generate entropy, and it'll be your entropy generated, and it's right here. Okay, well that's fine. And if I had a process where that didn't occur, and I had a temperature gradient in there, I'd be suspicious. Right? You should be suspicious, because that can't be. If we looked at the exergy, so now the exergy would simply be 1 minus T naught divided by T1 times Q. Okay? And we looked at the exergy out, which would be 1 minus T naught divided by T2. So now this is this quantity here, because this number now is bigger, right? So this total amount of exergy coming out, this is the exergy that's destroyed in the process. It's pretty clear, right? But you couldn't really have got that. If I'd asked you what usable energy have I destroyed, it tells you in here. I don't know why they saw fit to make this thicker than this. It should annoy you. Come on, Mark, you should be annoyed by that. And I'm too lazy to redraw the diagram, but they should have drawn this thicker than this, and then had this a little thinner, right? Because it must be less than 1. It can't be Q. It's less than Q.
It's T0 over T1, so they're not the same.
Right. Because T0 is your reference dead state. You always have this. You always have a reference state to do it. And this is the thing. When you start reading seriously about exergy, you have to clearly define your reference states. Okay.
But it seems like all those pink arrows, they share a common bottom level. So that's the only reason I'm using it.
Yeah, they should have just moved it. I think what it was, they got. I don't know why they did it that way.
T0 over T1 is bigger
Just
than T0 over T2.
2.
So,
T0 over T1 is smaller. T1 is a higher temperature.
right.
So this one comes out smaller. So what they should have done is and 1 minus T0 minus T1 is less than 1. right, times Q. So it's a picky point, but that's what it's supposed to represent. I'm sure they didn't think about it. It's the kind of thing I do when I'm not thinking about things. Okay. All right, we've discussed the work exergy difference between the useful work is the difference between the actual work that gets done and the work done on the surroundings. So, this would be P as atmospheric pressure and so on. We got exergy transfer by mass. It's just simply mass times the specific exergy that we talked about a little earlier. So, a couple of principles that come out of this, that if you have an isolated system, so I don't put any mass into it, I don't do any work on it, and I don't supply any heat to it, then the change in the in exergy of an isolated system when a process occurs is either equal to 0 if that process is reversible, or it's less than 0 if there are irreversibilities in the system, which in a real system that would happen. And that exergy is destroyed. Okay, so it's also true because this is identical to the change in entropy rule for an isolated system, can only be less than or equal to 0 depending on whether the system is irreversible or reversible. So anything that generates entropy also destroys exergy. And so we found a very simple way of saying that's all. When we talk about entropy generation and we're concerned with losses and efficiencies in systems and processes that unnecessarily throw away perfectly good usable energy, then we have to be concerned about, we can identify that with entropy generation. But now we can start putting numbers on the actual energy values. So it's just an account. If you think about it, it's a bookkeeping tool. It's not really a new property. We're just looking at that bit of energy that in principle was usable and then seeing how well did we do. And so let's see if we can. And then the exergy destroyed, and this is important, is always equal to the temperature of this dead state or reference state multiplied by the entropy generated.
And exergy puts things back in terms of units of joules, whereas with entropy, it's energy.
Right.
per
It's
Kelvin.
joules per. Yeah. It's confusing.
Yeah.
I mean, it's not. If we think about it, we can get it, right? And we know it's energy per degree Kelvin. But this makes it just a little more clear. Okay. Same rules, right? The decrease of exergy doesn't mean to say that a system cannot increase its exergy. It just says an isolated one can. But the exergy change of a system can be positive or negative during a process, but the exergy destroyed cannot be negative. Right? In other words, I can't just get that exergy back, is what it's saying. It's like entropy generated. It's an irreversible process. So if there's no exergy destroyed, it's reversible, which we've discussed. And if it's less than 0, it's impossible. But those you can tell by looking at entropy. Okay? Okay. Same kinds of rules that we apply to do the balances, so I won't drag you through all that. But if you look at the difference between the exergy entering and leaving a system, you subtract from that the exergy destroyed, that'll be the total exergy change in the system. Okay? And you just write that in any form you want. So again, just to reinforce the point, if this was to say total energy that was there, right? We're going to use this. Maybe it's a lump of coal, I don't know. Available to use would be this amount. This would be our exergy, and this would be unavailable from that energy source to use. Can't get it. All right? Then we do some process. Could be a natural process. It could be something else. And we have total energy out. We must, if it's a steady state, so this should be a steady state process. But of that energy that comes out, we may determine that this is the exergy out. Of that exergy out, this was lost. So this is the exergy out here, and then up to here was the original exergy in. This much here in red was lost. Remember, this was never available to us, right? So this is really the energy into the system. This is the energy out. This should be energy out, actually. Okay. This is Exergy out. This is the total energy that we thought we were putting in, but really it wasn't, a bunch of it wasn't available, right? So, you know, you don't burn every single little bit of that mass in the coal, right, for example. So who the heck cares about Exergy? And this is what I used to think until I started actually bothering to read about it. There are some really nice papers written by two guys that started to really get some major publicity early in sort of 2000 and so, and then took off. They're in Germany, Rosen and Dinser. This is more recent work that they did. They've got some rather crappy graphs from some earlier ones a little later. This is an example from one. We just go through it very quickly. So the calculations have all been done, so I won't bore you with those. But you've got a geothermal power plant. You've got the energy sources in water at 160 degrees C, and you're supplying it at a rate of, say, 440 kilograms a second as a heat source. And as a consequence of that, you're able to drive a heat engine that produces 15 megawatts of net power at 25 degrees C. Okay, so in your room. So if you go through and do some calculations, you can figure out the energy value of the source. It produces 251 megajoules per second, 251 megawatts, this flow rate. Its efficiency, if you look at its input to out, 15 to 251, and there should be no megawatts here. I don't know why that's there. Sorry about that. It's 6%, right? 15 divided by 6. I'll correct the slides before I put them up. The Exergy analysis shows that the source has a work potential of 44.5 megawatts, and I can supply you with those numbers. So the Exergy efficiency is actually 34%. And so it looks like the Exergy of the available water is only 18% of its energy, right? First off. The remaining 82% is not available for conversion. And then 34% of the available energy, or Exergy if you like, in the plant is actually converted to power. So 66% is lost. So now if I'm able to break down and understand why a certain amount of that energy wasn't available, and I see where the Exergy is being lost, maybe I can modify my process. It might require different devices to do that, and start to cut down on the amount of energy that's lost. And so what an Exergy analysis can do, if you start doing them in more detail, is help you identify pieces of your system that you could improve. And this could work just as well in solar or as anything else. Just look at what you're actually doing and how are we doing this piece of the conversion. Maybe you're using your device in a solar, if it's a solar thermal device, if you're using a collector, maybe like that. If it's solar photovoltaic, it's a little easier. But you may be, if you're using, ultimately, say downstream, you're using it to produce heat, you might look at why the heck you're doing it. It has nothing to do with your solar device. And if you're using a resistance heater, you may be wasting your time, as we'll see in a second here. Okay?
Where's
So,
where's the 18% come from?
oh, I got to show you how to get the 44.5.
So it would be 44.5 over 250.
Yeah. It comes from there. That's the Exergy. So I have to show you, if you want to know where the 44 point, I have to tell you how to do that. Okay. But, when you compare it, so first off, its actual efficiency, 6%. But we learn a little bit more here. But it doesn't mean to say it's better, right? Because here we're throwing away 66% of available energy. That's energy that was available to do work, right? In here, that 94% of energy that didn't get used, not all of that was available anyway. So it's good to know how much, because you have to. Then you know what you're limited to, because you don't want to beat your brains out trying to get 78%, and you couldn't. Okay, another nice one, space heater. So you've got a room at 25. It should be 25 degrees C, heated by a 2 kilowatt electrical space heater, and the outdoors at 21. Let's say the outdoors at 2. I'm sorry, so it should be 2. The heater has an efficiency of 100%. These things can convert that electricity to heat really, really well, all right? So you feel really pleased with yourself. No, you shouldn't. I just had this argument with a guy. I'm buying a new house, and it's energy efficient. And so it's in the south. And so you have a heat pump, And just in case it gets really cold, because heat pumps are not efficient when the temperature drops too low, it has a resistance heater in it. And it's 100% efficient. I said, this is ridiculous, right? And here's why. You remember how we defined the Exergy efficiency, right? It said for this device, so this would be, just remind you, no, it's too far back. Sorry. Okay, so in this case, we're dealing with the useful work to the reversible work, and if I use the heat pump to do the same job, so to take it, at 25 degrees C and the outside's at 2, not 21, I'd need about 0.144 kilowatts to get the same heat rate of the room. Because remember, I'm using a heat pump, so that's not my only input source, right? The Exergy efficiency of the heater is really 7.2% because I compare it to a reversible device that does the same job. That's why these reversible devices are useful. So now you think, I'm actually not doing that well. Right? It's not just a question of, the question really is, are you really using the best device to do the job? And it's kind of obvious, but like the builder in the South that convinced themselves that they're energy efficient. I said, well, actually, you're not energy efficient. You can do a better job because when the temperature drops, you're really going to be. It's 7.2%. I could do way better, 10 times better, right? With a different device. So you have to, it's common sense in this case, but it's not necessarily common sense that you'd be led to just by looking at efficiency numbers. So make sure you know what you're doing. So here's a diagram from another early Rosen and Dinser paper. And these guys have written some pretty good stuff. And they've actually they did an analysis of energy flow for Turkey. And so they've got hydraulic energy, so hydro, fossil fuels, utilities. They got the losses put in here. And they sort of calculate where they're used, industry, residential, transportation. And you looked at what's produced. So this is the energy out. What are considered energy losses in the system. And so they have energy products of around 680.6 units. I don't know what the units are in. Maybe it's gigawatts. It doesn't really matter. But when they look at the ratio of the energy produced to the energy inputs, it's about 41.4% efficiency. Now they're in petajoules. So these are petajoules per year. It's a lot of joules. Okay, here they look at it for Exergy. So they have the Exergy numbers up in here, go through the same balances, but now they look at what's produced in terms of Exergy. So useful energy produced is now on the order of 10 petawatts, and the Exergy lost is 73. This is not good, right? So their efficiencies come out in terms of their Exergy efficiency, which we would call their second law efficiency, is only about 27%. And they can start to look here. So here you've got very large losses in the residences, compared to the energy produced, right? And in industry, well, and you know why industry tends to do better than, say, people in homes and residences in terms of their energy conversion and their efficiencies and their minimization of waste? Have a simple guess. You'll go out of business if you don't. Today, everything's about keeping costs low, right? You could have the smartest idea anyone ever thought of in the lab, could be totally brilliant in terms of the intellectual thought required to produce it, but if that thing is too expensive, no one's ever going to buy it. So your next step is to say, okay, how can I find a cheap way to make this more, cheaper materials or whatever else? That's going to be your next big challenge. And industry has to solve that. It can't have that much waste. It's got to keep its bills down. That's why they do better, okay? In transportation, well, we just don't do as well, right? We're still somewhat inefficient in the way we transport things. But it's not as bad as heating and cooling homes, maybe. We're appallingly bad at that. apparently in Turkey. We are in this country too. If you go to Denmark, you'll find different figures. They're much, much better in their homes. They probably they just use less power than we do, and then they use that more efficiently. So the energy budgets for those places are much less. We just enjoy in this country very cheap power. It's cheap, especially electrical power. We could probably maintain that cost level if we can figure out how to use less of it. Our total bill, we wouldn't, per unit it might go up, but we'd be using less of it. Okay, and again, you see, where are the efficiencies? Energy efficiency. Hey, we're doing great residentially. No, you're not. Okay, so we could be thinking about why is that? Could go into so this tells you the next question is why is that, and then what are you going to do? Can you change it? Okay, utilities. I'm not sure whether this is put out really by a utility, but here they're doing a pretty good job of converting everything that's available to produce power. I probably because it's hydro. That's why. So if you're dominated by hydroelectric, and we just discussed, the Exergy value of potential energy is the potential energy itself. Your losses are just going to be, really viscous losses through the systems as it falls over the edge of something, and then there's going to be nothing until it hits the bottom again, and then you don't care. So just passing through the turbine, there's just going to be some frictional losses. So you can have very good efficiencies. I mean, turbines are very efficient, right? Let me just look at standard jet engines. They're hugely efficient. And actually, let's go back and look at that. No, I don't believe that, do you? Let's see, what's produced 105 to what went in was 468. That's not right. I have to come back and look at that paper. Am I looking at that wrong? I don't think so. It's the same. So what they're saying is, okay, we're using what we can. Everything else is unusable. Okay. So they can't do any better in these areas. And overall, we're doing it. So it looks like you could do better in residences. And that's nice because now it's where you're going to focus your attention. If you want to come up with some crazy piece of LNG technology that's going to make you your first million, well, you've probably got a higher probability looking in the residential area. And it's probably not surprising that's where a lot of government agencies across the world are looking. It's where the biggest waste is. Okay? And again, you sort of see the same here. Here's Exergy, this graph here is Exergy destruction. This is now done by source. So the red stuff is coal. And it looks like Exergy destruction is the worst. This is one of the worst offenders. What does this mean? It probably means that if you can find something like natural gas, which is, if we're looking back here, they got methane maybe. Yeah, electricity from methane. So let's say that's coal gas, and then there's natural gas also. I mean, it looks like it's a lot more. There's a lot less Exergy destroyed in that process. Not surprising that as we go to natural gas, regardless of the source of it, in this country, a lot of utilities are building natural gas-fired cogeneration type plants right now because they're more efficient and they waste less usable energy than in a coal plant. So that's kind of interesting in here. Okay, and a spin-off from, say, focusing on something which has less Exergy destroyed is, the coal-fired power stations have the largest carbon release also, which we heard in the other discussion. And look at the efficiencies. This is coal-fired plants. Efficiencies generally be lower, primarily because they're older, right? They're older plants, typically. I mean, like the thing over here, I think this is one of the worst, and it's the worst emitter in the Cleveland area, and it's pretty inefficient. But the plan here is to replace this with natural gas combined cycle, combined heat and power within the next few years. So it's just a little expensive, that's all. So what have we learned? We've learned that we can take some simple thermodynamics that we've understood from the first and second laws. We can recognize just by really reading undergraduate textbook descriptions of what all this stuff means and reminding ourselves that we understand it, and recognize that there's some energy you can't get at in a system's total energy. There's some energy that you can get at to use to do useful work. And now the question is, how efficiently can you use that to do work? And we call that usable energy exergy. Okay? You've seen just from those simple examples that this is not a bad tool if because you've got your head set to think about useful energy. So anything that you wasted that useful energy, now you're really feeling upset about. And you can now maybe target your systems or your sectors more effectively. So if I was thinking of making huge improvements in energy efficiency in the utility industry, it looks like their efficiencies for energy use and exergy use are about the same. So that's going to be a tough challenge for me, and the impact is going to be low. Whereas if I go to the residential work, it might be good. Now, there are other reasons to look at alternative means of dealing with utility scale power. And that is because we know that we may not always have, when we look at it by resource in here. You know, if I'm destroying exergy here like crazy because I'm using coal, and you know, there's a lot of waste from coal. There are other downside effects, and the other downside effect of it is it's fine when we're using it, right? Because we've got a lot of it. We can keep power costs relatively cheap using it, but at some point we run out of it. Now that may not be for 250 years, but we will run out of it. So what are we going to do about it? Well, that's what you guys are working on, right? You know, the best figure of merit is how much power. The best fusion reactor we have is the sun. And I always wonder why we worried about building a fusion reactor. We've got one. You guys have got to figure out how to access affordably the power that comes down to the surface. Solve that problem. Have people who work in chemical engineering solve the energy storage problem for utility scale storage. And now you've got some workable solutions without praying for fusion reactors, right?
And the second worst in terms of exergy destroyed is nuclear.
Yes. Which is interesting, right? Here's the nuclear is this one.
Yeah.
And then energy destroyed, exergy destroyed. Sorry, is here. Its efficiency is not bad, but that's because you chew up the source in a fission reactor, and what do you do with it after you're done with it? You can't use it again. Hopefully, I'll convince you that if you start to look at the energy balances in your system, and you're concerned particularly about efficiencies, or you're concerned about what areas should you target, it's not a bad idea to do the additional work and go through the additional confusion of actually looking at the exergy balances for the system, because it might give you some additional insight into that system that was a little bit harder to tease out. And so this is, I think I've become more interested in exergy in the last sort of year or two as a consequence of looking at sort of sustainability of systems, what are good things to target. So I think you should, if you're interested, you should, working in that area where you're really looking at system efficiency, system energy balances, take a look at the exergy also. It's a good idea. All right. So this is just to give you some laughs, I guess. So I know Callie introduced this Sankey diagram, and these, if you go to the Department of Energy websites, you see these great energy diagrams. It turns out that they were actually brought on around the late 1800s by a guy. He'd actually been a sea captain at some point, but he was analyzing a steam turbine, and so did something along these lines. But it turns out that the very first Sankey diagram was produced long before he came along by a guy who was tracking casualties during the Napoleonic War. And you can found this on the website. This is a guy called Minard. So this is Napoleon's excursion into Russia. And so the thickness of this line is how many blokes he started off with. And then the numbers in here is how many he's losing along the way. And you can see, you know, this didn't end well, right? In fact, the whole thing didn't end well, right? Because he gets to Moscow, he decides this is really not a good idea, runs away, and even in the process of running away, you know, they have terrible things. They rejoin these guys were smart, right? They got to this point and they just hid, and then they rejoined it, but guess what? They still don't do too well. And just because this guy was scientifically inclined, he also tracked the temperature along here and did not help him. But this is what they ended up with. This is what they started off with. I guess that was not a good campaign. Lost a lot of Exergy on that trip, because that was all potential energy, right? We shouldn't laugh. And I'll put these slides up, you can take a look at them, but if you look at these energy flow diagrams, these are from Department of Energy. If you look at these for different years, up to 2010, you can just sort of, you can tell what sectors are using more. You can even pick out the recession in these things and the impact it's had on power production. And I guarantee you, if you look at the ones for 2015, you'll see the impact of natural gas in these things. And if you look at 2025, you'll see even more. And if you look at other countries, like if you look at say the Arabian Gulf states like Dubai or something like that, you'll see probably by about 2020 they're importing large amounts of natural gas from the US to use in their power stations. So they don't have to waste their money burning oil that they buy themselves at $5 a barrel to burn in power stations, when it's much better to use natural gas, and they can sell that for whatever they sell, $100 a barrel right now. I think it's $98 a barrel right now. So they can make money by importing natural gas from us, and we're happy, I guess.
So we sell them gas and we buy their oil.
And this comes from, you know, you just think about it, in 2007, which is right after we started the Energy Institute, you know, in 2007, we were thinking there's not enough natural gas, man. We have to build all these liquid natural gas facilities around some of the major ports, New Orleans, New Jersey, and so on, because we're going to need them, because we're going to be importing it. No, we're exporting it now. We're actually already, I think, a net exporter. And that's just in the last 5 years. It's amazing, 6 years. How things change. And it turns out that this is probably good for us from an economic point of view, but it's bad from us from a complacency point of view, because just as we recovered very quickly from the oil shock in the 70s, unlike many other countries, and then ignored the fact that there may be issues downstream with cost primarily, as well as availability, we could have that happen again. So I hope that doesn't happen this time. And the thing to do is, you know, look at countries like Denmark's a great example, that really suffered in the 70s oil shock. I mean, they imported all their power from everywhere, right? And they decided they were never going to go through that again. And they've done a great job of diversifying how they do things. It's very expensive to own a car there. That's the downside. But it has to be, because they really don't want to be that reliant on one single form of transportation. So they've done a pretty good job of dealing with it. We're luckier than they are, because we've got lots of different energy forms. We just have to be smarter about how we use that Exergy.